both C6H14, then we can say, well, they're both, okay, so I guess technically I skipped a step. First is 1. So they're both nonpolar because they only contain carbons and hydrogens. So the intermolecular force we're talking about is LDF. And if there was just one O somewhere on either of these, all bets are off. We're not doing this because with one oxygen, it's going to be polar somehow. Okay. So now both nonpolar only, so we're talking that both of these only have LDF. 2, then look at molar mass. Because if they have different molar masses, then they will have different LDF. And the one with more molar mass has more LDF. But since they have the same formula, they're going to have the same molar masses. Everybody good so far? Anybody got any questions?
The only question I have, is this also true for ionic compounds too?
This is not true for ionic compounds. So,
okay.
Right. So that's why so there's sort of like 3 things. I know we're doing a lot of things with intermolecular forces, right? One of them is first determine if they have LDF, dipole-dipole, hydrogen bonding, or ion-ion, because that'll tell you straight away which one has the stronger IMF. But there's 2 cases where you can have 2 species that have the same type of intermolecular force, and then we have to know how to tell them apart still. And we'll do more. There's a whole question coming up just about the trends in ion-ion forces. And the short answer is right now, it does not depend on molar mass at all. All right. That's a good question. So then 3, which is where we were on the other side, says, so if they have the same molar mass, then look at which is more spread out. And because the more spread out it is, the more intermolecular forces it can have with a neighboring molecule. So, and I'll write that. So, more spread out equals more or larger LDF. And our picture of this is if I have 2 of these, and it doesn't matter how you draw them, but let's just draw it like this. So, and you look at the length of interaction or the surface area of interaction for this molecule with another molecule of the same versus and really all we're looking at here, and it is enough, so this line, this dashed line, is longer than this dashed line. This one is more spread out. So it has larger LDF. And I can't remember the example I gave in the lecture outline, but I think I gave the boiling points and how they were different. And remember, larger intermolecular forces, whether it's LDF or any of the others, has higher boiling point. Higher boiling point, higher melting point, higher heat of vaporization, higher heat of fusion, higher surface tension, higher viscosity, and lower vapor pressure. Anyway, Daryl, I don't know if that addresses your question. I'm happy to talk more about it if you'd like, or do another example.
I'm good.
Cool. Any other questions about this?